Alright, in this series of videos we're going to cover the material in chapter 20, and this material has to do with thermodynamics, and we're going to talk about this topic of entropy, which we'll represent with the symbol S. We'll talk about free energy, which we represent with the symbol G, and then basically we're going to be talking about which direction are chemical reactions favored, and ultimately it's this guy right here that's going to determine the direction of chemical reactions. And entropy feeds into this, and enthalpy feeds into this. So we're going to talk about how free energy, where free energy comes from. It comes from a combination of these two. And so we'll talk a little bit more. We've talked about enthalpy, the H. So here we're going to talk about entropy and give you an overview of what that is. Now we'll do this basically in a series of sections. So sections, and what we're going to do in this series of videos is I'll break them down at least into sections. And so there may be some sections, if they're a little bit longer, I'll break them down into like some smaller subsections. But we'll cover the second law of thermodynamics, which basically has to do with predicting spontaneous change. And this guy also has to do with entropy. Then we'll talk about how to calculate change in entropy for reaction, and then we're going to talk about the relationships of these things together: the entropy, the free energy, and the work. And so, and then finally, on this last topic, we're going to talk about how free energy, our G, is related to equilibrium, right? So, equilibrium position, our equilibrium constant, is related to what the free energy of a reaction is. And so we'll talk about those things, and of course which direction will a reaction go when it starts. Well, that will depend on this guy as well. Basically, which direction do you have to go in order to reach equilibrium. So let's start by discussing spontaneous change. And so of course this is a change that occurs without input of energy. So we define this here. We talk about the continuous input of energy from outside of a system, and that would basically be just to give you an example of a spontaneous change. Say if you have water, you take a container of water, and put it in a situation where it's at a pressure of 1 atmosphere, and we're at a temperature below 4 degrees Celsius, then the spontaneous change for that water is that it will freeze. You put water at 1 atmosphere below a temperature of minus 5 degrees Celsius or minus 4 degrees Celsius, and you will get freezing. And that would be a spontaneous process. Now, all chemical processes require energy to take place. So this is where we talk about activation energy. But a spontaneous change, once it's begun, does not require input of energy. Now, the opposite of spontaneous would be non-spontaneous. And so non-spontaneous change will occur only if a continuous supply of energy is given to the system. Now, so for a reaction, the spontaneous direction will only be in one direction. So if a reaction is spontaneous in one direction, then the opposite reaction, or the reverse direction, will be non-spontaneous. And so these are some important concepts to keep in mind. Now, another thing that I want to emphasize here is that spontaneous does not mean instantaneous. Okay? So spontaneous does not equal instantaneous. And so, what spontaneous will tell us is the direction something will go. It doesn't tell us how fast something is going to go to get there. What really tells us about how fast is here. So this will tell us about the speed of a process, and this tells us about the direction. Has to do with whether or not it's spontaneous, and of course whether or not something is spontaneous has to do with the energy associated with the process. All right, so what we find in looking at the first law of thermodynamics is that it does not predict spontaneous change. Now, what is the first law, so you might ask? Well, basically, it's this guy right here. The the first law of thermodynamics is stated here. Energy is conserved, so in any process that takes place, energy is conserved. It's neither created nor destroyed, but it gets transferred. And so it can transfer, it can change form, but is not created or destroyed. So energy is something that is conserved. And so we can represent a change in energy as as heat and work. So the sum of heat and work give us the change in energy for a system. Now, for the universe, and here the universe just is simply all that exists physically in our, basically where we live is the universe. It's everything. It's all the stars, all the galaxies, it's everything. All of space and what space contains is the universe. So it's basically all matter and energy. All of it. Everything. That's the universe. Now, what the conservation of energy means is that the change in the energy of the universe will be zero. So if energy is neither created nor destroyed, as we said right here, if it's not created or destroyed, then what that means is that the total energy of the universe is constant. Now, the law of conservation of energy applies to all changes, and but it does not allow us to predict the direction of a change. So, what we're going to do is see what does, but basically what we want to first of all talk about what doesn't allow us. And so here, this law of conservation of energy, it applies to all changes, whether they're that occur within the universe, but basically it tells us that the sum of all of these changes, so if we've got the change of energy of surroundings or the change of energy of the system, then basically the change in energy of the system and the surroundings together give us the change in energy of the universe, and the overall change in energy of the universe will always be zero. That's what the law of conservation of energy tells us. Now, also, when we talk about enthalpy change, sometimes we tend to think of enthalpy change, or delta H, as a predictor of a spontaneous change, and it turns out that it does not predict that. All delta H tells us is that you have an exothermic when delta H is less than 0, and you have an endothermic when delta H is greater than 0, but it does not tell us whether or not a change will be spontaneous. So what we have is some examples of things that are spontaneous exothermic and spontaneous endothermic. So an example of a spontaneous exothermic would be freezing and condensation at low temperatures. Combustion reactions are spontaneous exothermic, where our delta H is less than 0, and then oxidation of iron, other metals, another example. Now, there are, and this is where, so this one is not so surprising, this first point up here, but sometimes people find this part a little more surprising, and that is that spontaneous endothermic processes exist. And so this can be melting or vaporization at higher temperatures, or dissolving of the most soluble salts. So what we find is that the sign of delta H does not predict the direction of spontaneous change. So we'd have to look elsewhere to think about that. And part of what we want to do here is discuss the role of entropy in contributing to spontaneous change. All right. Now, all spontaneous endothermic processes result in an increase in the freedom of motion. So the examples that we gave previously, melting or vaporization at a higher temperature, these are spontaneous endothermic processes. So what we find is that if we move from the solid state to the liquid state to the gas state, we have dramatically increased the freedom of motion of particles. So we are increasing the freedom of motion in moving from this state to this state to this state. Similarly, if we move from a state where we have a crystalline, solid, and liquid to having ions in solution, we've moved to a situation where we have less freedom of motion over here to where we have more freedom of motion over here. And so a change in the freedom of motion of particles in a system is very important in determining the direction of a spontaneous reaction. Now, where we're going with this freedom of motion and relationship to energy, we want to go through this concept of microstates. So just like we have electronic energies in an atom, we can describe them as quantized levels, energy levels. A system of particles also has what are known as allowed energy states. And this allowed energy state for a system of particles is referred to as a microstate. And therefore, then, at any instant, the total energy of a system is dispersed throughout microstates. And given a set of conditions, each microstate has the same total energy as any other microstate. So this would basically be a system of particles that are in different energy states themselves. Well, then the individual particles being in different energy states will add up to a total energy state for the system, and it would be a quantized energy state for a system of particles. So each microstate at a given set of conditions has a equal likelihood. Basically the probability of each microstate is the same. Now, the larger the number of microstates we have, then there are more ways in which the system can disperse its energy. And that is a favorable thing. So this basically is a good thing for a system. So if you have a way in which you can disperse the energy more broadly, then that larger number of ways in which a system can disperse basically means we have more. It's correlated to a larger number of possible microstates. So now I want to get to defining entropy. So what we have is entropy is defined in the following way. So basically, we have a given number of microstates in a system that we represent with this capital W here. So basically, given a particular number of microstates, entropy for that system can be calculated by taking this guy here, what is known as the Boltzmann constant, and multiplying times the natural log of the number of microstates. Now K is called the Boltzmann constant. And K is equal to the universal gas constant, R, divided by the Avogadro's number, which we use as NAV. So basically, the universal gas constant here, R, universal gas constant, and Avogadro's number here as basically the 6.022 times 10 to the 23rd, and R is our universal gas constant. So the Boltzmann constant is a constant, and it basically comes from these two constant values that we have, the universal gas constant and the number of particles in a mole, right? So Avogadro's number. Now, and this is where I really want to make some emphasis here. A system with fewer microstates then has lower entropy, and a system with more microstates has higher entropy. So the more microstates you have, the higher the entropy. Now, all spontaneous endothermic processes will have an increase in entropy. So basically our delta S will be positive for all spontaneous endothermic processes. Now, one last point on entropy is that entropy is like enthalpy in that it is a state function. It just basically has an initial value and a final value. And that initial value and final value is independent of how you get there, right? Now this is different than work. Work depends on direction, and heat depends on the direction of heat flow. But enthalpy is a state function, and entropy is a state function similarly. Now, we get to the second law of thermodynamics. And the second law of thermodynamics is stated here, and then we give a mathematical representation of it. So for the sign of the change in entropy does not predict the direction of a spontaneous reaction by itself. But we do know with respect to change in entropy is that if we consider both the system and the surroundings, we find that all real processes occur spontaneously in the direction that increases the entropy of the universe. So if we're talking about the entropy change for a system or the entropy change for surroundings, those can be positive and negative and so forth, but the sum of these two together for any process that occurs in nature, that occurs spontaneously, any spontaneously occurring process, then the overall entropy of the universe increases. And that's basically the second law of thermodynamics. All processes, all spontaneous natural processes result in an increase in the entropy of the universe. Now, we know that there are times when the entropy for a system or the entropy of surroundings can go down or go up, can be positive or negative, but the overall entropy of the universe will always move in a positive direction. So what that means is this last point here. So if we have a process that is spontaneous, a decrease in the entropy of the system. So if the system goes down, then the surroundings must increase by a larger amount than the system goes down. So we can have a system that has that will change in such a way as to have fewer microstates. But basically, if that happens, then we're going to have the overall entropy of the surroundings goes up. And it doesn't go up by the same amount. It goes up by a larger amount than the change in entropy for the system. And so that's basically the mathematical representation of the second law of thermodynamics. Okay, now I want to go through a little comparison here of energy and entropy. And so from the first law, we basically get this. So this is our first law of thermodynamics. The total energy of the universe remains constant. And that's for all processes. So here we've got our second law of thermodynamics, and basically, which we talked about just previously, the total in any spontaneously occurring process, the entropy of the universe will increase. Now, the difference between total energy and the total entropy is interesting in this for these 2 points here. When we talk about energy, delta E, we oftentimes will use enthalpy to approximate it. And so for enthalpy changes, it turns out there's no 0 point. We can only measure changes in enthalpy. There will not be a 0 enthalpy because the overall, so energy is neither created or destroyed, so you can't destroy it and go all the way to 0. So you have no 0 enthalpy. Now you could have a 0 change in enthalpy, but you cannot have a 0 enthalpy. So the next point, though, is that, however, for entropy, there is a 0 point, and we can actually determine absolute entropy values, although we can't determine absolute enthalpy values. We can only determine changes in enthalpy. Now, and then we'll find out later that our enthalpy will oftentimes then even be referenced. We'll have standard states, and we'll do that for entropy as well. But I want to go on and address this concept that entropy can have a absolute value. And it turns out that there is a third law of thermodynamics. Sometimes people don't realize this, but this is our third law of thermodynamics. And that is that a perfect crystal has 0 entropy at absolute 0. And what we mean by this is that if you have a perfect crystal with a flawless, basically all of its particles are aligned perfectly, and if you were to lower the temperature of that crystal all the way down to absolute 0, the particles will have a minimal energy, so there would only be 1 microstate. And if there's only 1 microstate, we have the natural log of 1 is equal to 0, so entropy equals to 0 at absolute 0 for a perfect crystal. So then to find entropy of a substance at a given temperature, we're basically going to cool it as close to 0 K as we can, and then we heat it in small increments. And because at 0 K, we're going to have a really low number of microstates, and our entropy would be as close to 0 as you can get. We then heat in the small increments, and we can calculate from heating up from 0 K, we can calculate delta S from measurements of heat and temperature required to get to those higher temperatures. So basically then the sum of our delta S values gives us an absolute entropy at a particular temperature of interest. So we can have absolute entropy values, although we will not have absolute enthalpy values. We have relative enthalpy values. So what are the implications of this? Well, one implication is that we can define a standard molar entropy for a substance, and it's measured for a substance in the standard state. So the units of a standard molar entropy will be joules per mole times Kelvin, or per Kelvin if you. So this is going to be joules over moles times Kelvin, like that. Now the convention for defining standard state includes, for gases, we will be at 1 atmosphere for the gases. For a solution, we will be at 1 molar for solution. And the convention for the standard state is that the pure substance will be in its most stable form for solids and liquids under these conditions.